When you find yourself in a foreign city as a tourist, you often keep your eyes open for waymarks, signposts that tell you where the local attractions are. For example, if the city has a famous cathedral, you may see a signpost that points you in the direction of the cathedral. And when you start walking in that direction, you may see another waymark that tells you this is where you have to turn right. And then you follow that road and you may see yet another waymark until you eventually reach the destination. The same if you want to then go to the main bus stop. You may look for these waymarks and again follow the path that is indicated in this way. Now that is very similar to routing that occurs on layer 3. And these waymarks map out the city in a static manner. Chances are that the cathedral will probably not move, that the main bus stop will probably not move, and so on. However, if you find yourself in a sort of wonderland environment where things start moving around, then you may need some magic to adjust these waymarks so that they point in the new direction. In fact, even in an ordinary city, it's possible that a certain waymark points you to an attraction via, let's say, a bridge. And then the bridge collapses and the waymark is now wrong because it directs you to cross the bridge. Again, it would be nice, it would be magic if the waymarks in the city were able to adjust themselves so that they point you to a new route. As I said, on layer 3, when we do routing, the packets essentially follow such waymarks, things that have been put in place. However, we need something that will put these waymarks in place automatically, and things that will adjust according to the changes in the environment. In our case, specifically changes in the network, whether it's the topology that changes because a certain link is down, or whether it is other conditions that change, such as congestion that increases on a certain link. You may need something that will adjust these waymarks for you. Now, those waymarks we will refer to as routing tables, and the applications that will update these waymarks or these routing tables are known as routing protocols. The routing protocols operate on layer 7. Each one of them is an application-oriented protocol that is able to adjust the waymarks, either globally throughout your network, or in our analogy, throughout your city, or just locally, so that when it knows it points in the wrong direction, it adjusts itself, and hopefully the others will follow suit, and soon you will have a new path to your destination. In this video, we're going to look at these layer 7 protocols. These are application-oriented protocols that adjust the routing tables so that the optimal routes are available, such that layer 3 is able to only forward packets without really thinking about the best path. To move the example that we mentioned in the introduction a little bit closer to networks, let's consider a tiny network. In this network, we only have 4 nodes, and they are labeled A, B, C, and D. And these nodes all have routing capability. They are all able to forward packets to one another. And as you can see, when you look at, let's say, node C, we have a routing table there that tells you if you want to go to A, then move, in our example, northeast. Or if you want to go to B, also move northeast. Or if you want to go to D, then move straight east. Clearly, in a network, we won't use these directions. We would use something else, and we'll talk about that in a moment or two. But before we do, let's just quickly bring the other waysigns into the picture. They hopefully all make sense. So just by way of example, if you have a message at node A and it needs to get to node D, then the routing table at node A will say, well, go east if you want to get to D. When it gets to the next hop, that would be node B, it can look in that routing table that tells the packet to move southeast. And then suddenly it is at its destination. It has arrived by simply following the indicators in these routing tables. Just as an aside, you can see that there are alternative routes to get from A to D. It would have been possible to go from A to B to C and then to D. But for some reason, that was deemed to be the longer option and not the one that was indicated by these routing tables. To make this example slightly more realistic, instead of using compass directions, we will actually use the notion of next hops. So what you will see in the routing tables now are no longer the compass directions, but what the next hop is. So if, for example, you want to go to A and the message is at node C, then if you look A up in the routing table, it tells you the next hop is B. So if C can send that message to its neighbor B, it will arrive at B, and at B we will look again in the routing table, and that will tell us, well, if you want to go to A, just send this to A. That is the next hop. So in every case, it tells you which the next hop is, and every machine will have to know how to get to its neighbors. Those are the two simple requirements for this algorithm to work. Now, let us quickly talk about the reasons why one may choose a particular route. Obviously, one will choose a route because it gets you to the destination. But often there are costs involved. And the cost may be an actual cost. There may be a financial cost to send a message via a link. But more typically, the cost will be something like, let's say, the network speed. If the link between what we had in our previous example, nodes B and C, if that link is really, really slow, then you may want to avoid it unless you cannot avoid it. Or perhaps more positively, if the link between C and D is really fast, you may want to use that as often as you possibly can. We can also look at congestion. If there is a lot of congestion, in other words, many data packages on the link between B and C, you may want to avoid it. It's pretty similar to navigating with a GPS navigator. When you're driving, you may see that certain parts of the route you want to use happen to be congested. On many apps, it will be indicated in red that part of the road is very, very busy, or even that there's been an accident and no traffic can get through. Then you will choose an alternative route. And what you have there are, number one, costs. So the congestion is a cost. And number two, it may be dynamic. A route may be very open right now, and a couple of minutes from now, it may be very congested, and you may want to adjust your routing dynamically. You may not want to take that route that just now happened to be a good road, but now suddenly is congested, and because of that, you may want to change your plans and take another route. Here we are thinking about dynamic versus static routing. The one is where once you have a path, that's the path you follow. The other one is dynamic routing. It's where you change your plans as and when necessary. In what follows, we will talk about the protocols that establish those routing tables. There are other mechanisms they can also use, but our focus will be on routing tables. What we will have to do is to introduce a couple of new terms because different terminology is employed in this context from what we used to employ. And in fact, the notions that are denoted by this terminology is also somewhat different from what we did previously. In our simple example of routing, we were routing packets from one machine to another, from A to D or something like that. Routing from one host to another host is indeed possible. It is indeed something that happens. However, in general, we want to route packets from one network to another network. If you think about it, the name of the internet indicates that it is an internetwork, that it is a network of networks, that we want to be able to link those networks and then route packets through these various networks up to the point where they should be, their actual destination. In those networks, we will typically employ computers that have a special function, and those computers are known as routers. So every network will have its routers, and we will then pass the messages from one router to the next. And when it gets to the final network, then there will be some mechanism where you can just get it from that router to the final machine. That's something that we will consider later. However, even when we talk about routing from a network to another network, we are not completely at the point how it actually works. How it actually works is that networks are often combined into larger entities that are known as autonomous systems. In the case of large corporate networks or large university networks, they are typically large enough to form an autonomous system on their own. So in that case, a network and an autonomous system may be the same thing. However, if you have two smaller university campuses right next to one another, they may decide to manage their network combined, and they may group them together into a single autonomous system. If you begin to think about the services provided by an ISP, an internet service provider, then the ISP typically may be serving individual users, it may be serving small companies, and it may be serving large corporate users. That ISP may treat its entire network, including those that belong to its customers, as a single autonomous system. Or it may group, let's say, the individual users together and treat that subnetwork as an autonomous system, and then possibly group the small companies together and treat that as an autonomous system. And then for the large corporate users, they may treat every company as an autonomous system. So exactly where you draw the lines between a network and an autonomous system is not always clear, but in the practical context, it usually makes sense when to group networks together into a single autonomous system and when to keep them separate. The important reason why we are introducing this notion of autonomous systems is that a lot of the routing occurs between autonomous systems. In other words, from one autonomous system to another autonomous system. On the other hand, a lot of routing occurs within an autonomous system, inside an autonomous system. And the routing that is employed in these two cases is very, very different. To introduce another term in this context, the protocols that determine routes are often known as gateway protocols in this context. So we don't call them route determination protocols. Very often we will call them routing protocols, but as a synonym and one that is perhaps slightly more clear in exactly what it means, the term gateway protocols. The protocols that are used inside an autonomous system are known as the Interior Gateway Protocols, IGPs. The protocols that are used outside an autonomous system, or rather than to route packets between autonomous systems, are known as Exterior Gateway Protocols. The primary difference between the Interior Gateway Protocols, or IGPs, and the Exterior Gateway Protocols, or EGPs, is the fact that on the inside, you typically want to achieve the fastest, cheapest route, however you measure fast or cheap. There is some metric involved, and you want to minimize that metric so that you can get a really cheap, low-cost connection, and the low cost may be something like a cost in terms of time. We will return to the notion of cost soon. However, when you look at exterior gateway protocols, there may be other factors. Usually there are other factors involved. For example, two ISPs, two internet service providers, may have a special agreement that they are willing to carry traffic on behalf of one another, and therefore the exterior gateway protocol will prefer to use this partner network rather than another network to forward its packets to, let's say, overseas. So almost commercial or sometimes even political decisions that impact on the exterior gateway protocols, not the speed of routing, but the contracts and other things that may be in place on a business or even governmental level. Let's turn our attention to the interior gateway protocols, the IGPs. These protocols use the well-known routing algorithms. The two algorithms that are best known are, number one, the Dijkstra algorithm, and it's named after its inventor, Edgar Dijkstra. And the other well-known algorithm is the Bellman-Ford algorithm, which is named after the two people who invented the same algorithm more or less at the same time. I assume that most viewers are familiar with these two algorithms, and I will therefore not discuss them in detail in this video, but I will produce two supplementary videos in which I will briefly recap how they work so that those who are not quite up to date with their operation can catch up. The Dijkstra algorithm, as you know, or if you don't know it, is typically associated with a centralized approach to routing. In other words, it works best where you have this bird's eye view of the network and you can determine routes because you know everything you need to know about the entire network. In contrast, the Bellman-Ford algorithm is typically associated with distributed routing. So every node has a very small view of its particular little environment. In the Bellman-Ford algorithm, every node knows something about its neighboring routers, its neighboring nodes in this routing context. It doesn't have this global perspective at all. So decisions are made locally, not on a global scale. In addition, the Dijkstra algorithm is typically associated with static routing. That is where you determine a route once, and once it has been determined, you keep on using it. In contrast, the Bellman-Ford algorithm is typically used where you use dynamic or adaptive routing. In other words, the Bellman-Ford algorithm is quite able to deal with situations where the network topology changes and it can adapt its routing decisions based on the changes in the network. However, having said that, this does not prevent us from using the Dijkstra in a distributed and even a dynamic manner. In fact, the very first protocol that we will discuss in a bit more detail will do exactly that. So let's talk about our first example of two examples of IGPs, Interior Gateway Protocols. And the first example is the Routing Information Protocol, or RIP. RIP is based on the Bellman-Ford algorithm. In order to get a RIP router to work, you just have to tell it who its neighbors are, specifically who its router neighbors are. That typically means that you have to tell it what addresses are assigned to each network interface cards and also the ranges of those addresses. In other words, it's the pool in which that interface card sits with its address. Now, assume that you have a RIP router. Typically, that will be either a purpose-built box, or it will be, in most cases, a Linux or perhaps Unix computer with the necessary software installed, and in particular, on which the RIP software has been installed. Now, if you take that router and you plug it into its various networks, it will start to exchange its routing tables with its neighbors. Initially, this new router will have no routing table to speak of. It will just know what the neighboring routers are. But with the moment when it gets a routing table from a neighbor, it will know which nodes are reachable by that neighbor, and therefore it will know which networks it can reach via its neighbor. The metric that is used by RIP is the hop count. So the cost of any link happens to be 1, and there is no possibility to say that it should rather not use a specific link because all links are deemed to be equal. So what this means is if I am sitting at a router, and let's say this is router A, and there's a neighbor, and that happens to be router B, if B says, I can get to C at a cost of 5, and it tells A, I can get to C at a cost of 5, then it means to get to B is 1 hop, and then another 5 to get to C. So A knows after it receives this routing table from B that it can also now get to C. Previously, it didn't even know that C existed, but now it knows that it can get to C at a cost of 1 plus 5. That's plain old Bellman-Ford algorithm with the simplification that the cost of links are always 1. We don't have links at different costs. Every edge in that graph is associated with a cost of 1. RIP has seen a number of incarnations, the original RIP protocol, and then RIP2, and also RIP-NG, and so on. And what happened in these various versions was mostly an upgrade of the security features. In the initial version, it didn't have any security features. So if you were a malicious user, you could plug in your own router, RIP router, and suddenly it would start attracting traffic, especially if you advertised the routes that were really cheap. Then packets would flow through this rogue router. But in the later versions of RIP, security has been beefed up. Also, in the later versions of RIP, better provision for how to deal with the address space has been made. We will only talk about networks and subnetworks and super networks when we get to layer 3, but the original RIP wasn't really good when it had to deal with subnetworks. It could only split network addresses on byte boundaries. In the later versions, it has greater flexibility in that sense, and in the most recent versions, it also makes provision for IP version 6 in addition to the IP version 4 that it supported earlier. So RIP is a rather easy router to use. You don't really have to assign costs because you're using hop count, which is very easy to determine. And since it uses Bellman-Ford, it is by definition adaptive or dynamic. It can adapt to new network conditions, and it basically learns the network topology just from its interaction with its neighbors. Obviously, over time, as information is exchanged, it learns more and more about nodes or about routers that are further afield in this network. However, the exchanges typically occur every 30 seconds, the exchanges of these routing tables. So if you have a big network, then it means it's pretty big routing tables that are exchanged every 30 seconds, and that may itself cause a load on the network that you did not anticipate. The next interior gateway protocol, IGP, to consider is Ospf, Open Shortest Path First. So the name sort of gives us an indication that it wants to find a path that is open, that is not congested, and we're going to use that one. Now that's just a very broad gut feel definition of what happens there. More specifically, if you want to make this formal, Ospf is an example of a link state protocol. So it gets notified about the states of the various links in the network, and the states may be that those links are down, or that they are congested, or more positively, that they are really fast and that they are really coping well. Ospf uses the Dijkstra algorithm. So we would expect it to operate in a centralized static manner. But that's the very last thing that Ospf does. What Ospf does is it distributes the entire network topology throughout this network. In other words, it broadcasts it to every router in the system. And therefore, every router does have this bird's eye view that we needed to use Dijkstra. And we can step away from the idea that it has to be centralized. Every node has the big picture. And every node is therefore able to determine the routes, the best routes, from it to every other node, or every other router then, in this network. We also said that Dijkstra happens to work best in a static environment, but what happens in Ospf is that the calculation of routes are repeated. So once you've repeated the calculations to determine the cheapest routes, you just do it again, and if you get a different result, that is the new routes. So you update it by repeating the calculation of routes. Ospf was introduced because the hop count metric that is used in RIP was not sufficient. In Ospf, they said, we actually are interested in things like link being congested so that we can avoid it, or link being really fast so that we can use it, or in the worst case, perhaps a link being down so that we can avoid it. In that sense, they wanted to assign costs to the various links. And the cost would be an indication of the cost or the inverse of the benefit we can get from using that link. So in some cases, cost may be actually a financial cost, but more generally, a link that is congested will be deemed to have a high cost because your traffic will pass very slowly through it. On the other hand, a link that happens to be very fast, perhaps it runs at 10 gigabits per second, or perhaps it just happens to be uncongested, it happens to be clear, that will have a very low cost because your packets will traverse it very quickly. And in that sense, you assign costs. And costs can be anything else. So if your network calls for a different costing model, then that's what you do. You assign costs differently. Once you install your Ospf router, it will get a picture, an image of the entire network topology from the rest of the network. It needs that to be able to work. and it will be informed about the costs that are currently applying to all the links in the network. And that's the basis on which it then starts running the Dijkstra algorithm and calculates the cost of routes to everywhere else. In the end, Ospf caters very well for this environment where everything is not uniform. It adapts rather fast to changing network conditions. In fact, most network engineers prefer to use Ospf rather than RIP if the network topology or the network links do change regularly, because it tends to pick up those changes in the network conditions much faster than RIP does, even though the algorithm that it uses is not ideal for that. There are a number of other IGPs that we can discuss, but our intention is to cover the field broadly, and therefore we will not spend more time talking about IGPs. It's time to move on to EGPs, Exterior Gateway Protocols, the protocols that we use to route between various autonomous systems. And now we have to introduce a couple of additional terms so that we can talk about EGPs. As you know, EGPs enable autonomous systems to talk to one another. But how do those autonomous systems link to one another? The term that is used for linking autonomous systems together is known as peering. This peering has nothing to do with the peer-to-peer communication in the 7 layers of the ISO model. It is an entirely different use of the notion of peering. Peering typically occurs at some specific location, at some specific internet exchange. In South Africa, we have 3 of those internet exchanges that are very, very popular. The biggest one is the one in Johannesburg, which is known as the Johannesburg Internet Exchange, JINX or JINX. And it's by far the busiest one in the country. That's where all the ISPs connect their networks together, and they get their traffic to flow from a particular autonomous system to another autonomous system, or from one ISP to another ISP. If you look at the members of JINX, the parties who peer there, you will typically see that it refers to ISPs. Our second busiest internet exchange is the one in Cape Town. So that is the Cape Internet Exchange, CINX or KINX. You don't want to send traffic up from one Cape Townian ISP to Johannesburg and then back down to Cape Town to reach its destination. If the source and the destination of a message are both in Cape Town, then, well, you're just going to interchange the network at that peering site in Cape Town. And then the final one that we have in this list of internet exchanges is the one in Durban, DINX. I've never heard people say DINX, but I guess that's how you would pronounce it. And the same logic applies. Now, if you are sitting in a very small town, then it may well be that you will be sending your traffic, let's say, to Johannesburg and then back to another ISP in that small town. You cannot have internet exchanges everywhere. There are also a couple of internet exchanges that are not generic in the same sense that the 3 that I've just mentioned are. The 3 that I've just mentioned is more or less open for anyone who wants to join them. You just have to abide by their rules, pay the necessary fees, and you can then start to interchange or peer with other networks or other autonomous systems. However, we also do have internet exchanges that exist because of agreements that are in place between specific ISPs. And the South African Internet Exchange, SAIX or SAIX, is one such example that you may want to look at. In a very similar sense, it may be worth your while to Google the nation of a carrier hotel. That is a building that sort of serves as a hotel for various carriers or ISPs. And in one very interesting TED Talk, you will see how various parties try to get as close as they possibly can be to Wall Street, because they want their trade messages to go through to Wall Street in the absolute smallest amount of time possible. And therefore, you will find that a lot of the buildings around Wall Street are empty. There are no people living there. There are no people working there. It's all full of equipment, because that is the ideal location for these carrier hotels that have to operate there. But that is a topic that you can explore on your own. We won't go into any details. What we need to talk about, though, is an example of the protocol that is used for such peering, or stated differently, an example of an exterior gateway protocol, an EGP. And the best example is BGP, the Border Gateway Protocol. And the Border Gateway Protocol is one that implements all these business and political and other decisions that you have to make in terms of how you will route messages when you peer with various other ISPs. As we've noted previously, the reasons why you may want to forward your messages via a specific ISP often do not depend on speed alone. It depends on the contracts and things that you have in place. Let's say you want to get a message out to another continent, then you can look at who owns the various fiber links, the various undersea cables that connect South Africa to the outside world, and you will see that some of the cables are operated by specific ISPs, while others are co-owned by a number of ISPs. Now, chances are that if you want to use the cable that is owned by a specific ISP, that you'll have to pay them to carry your traffic. And therefore, you may want to use a different service. However, the moment when that undersea cable gets broken, or any undersea cable that you're using gets broken, you may have to fail over to the one that you didn't actually want to use. But then you also may want to throttle your traffic to keep costs low. So the decisions become really interesting. There are very few people who know how to properly use BGP. And unfortunately, I cannot claim to be one of the people who know how to operate it. I simply don't have experience on that level of interconnection. I do know about a story that I've read in a book where someone configured the border gateway server of a particular ISP incorrectly, and suddenly all the internet traffic intended for that country was sent to a different country. Now, whether that story is true or not, I don't know, but I do know that mistakes in the configuration of BGP routers can be very costly, and they can create connectivity issues for countries even. So that is definitely something where you can upskill yourself if you want to know something about a network skill that clearly is a very scarce skill. To make this slightly more practical, let's look at a couple of cases where one uses routing or can access routing in a typical context. The first context here is a normal personal computer that usually does not perform much routing at all. On such personal computers, whether they're Unix or Linux, doesn't really matter, there is a root command, and if I enter it, it will provide me with information about how to use it and so on. And you will see that this is a command that is intended to manipulate routing tables. And what you can do are things like adding different routes, for example, add some interface and assign an address to it and tell it where it will send packets to and so on. You can also delete entries from the routing table or modify entries in the routing table. The challenge in this particular example is that because it is a personal computer, there is not much routing that occurs at all. Personal computers are usually at the leaves of the tree, so one would use them to just send messages to some default router, and the default router will then take it from there. If you looked carefully, you would have seen that one of the commands that we can do is something like root print. And that particular option that I've highlighted is intended for IP version 6. If I just use it in general, then I can say root, and that is followed by print. Again, we see a lot of information scrolling across the screen, and there is the point at which we entered it, and you can see that it starts with an interface list. So there are quite a couple of interfaces on this particular computer, and in principle it is therefore possible that it will perform routing. It can, for example, do routing between its Ethernet port and its Wi-Fi port and so on. But as I said, most personal computers are not configured to do that at all. Here you can see the IP version 4 root table, and most of it routes to machines that are on link. In other words, either something that happens to be this exact machine or one of the interfaces that happens to be on this machine. So it doesn't even have to forward it to anything. They are just sending it out via a particular link. The only real routing entry here is the top one there. And in that particular example, that one routes to the default gateway. So you can see the default gateway listed, and the meaning of this particular IP address and net mask will become clear when we discuss layer 3 protocols. That is more or less it on a typical personal computer, but we can look at a router to make this just 1 degree more interesting. Here we are logged onto a router. This happens to be a Ubiquiti Router, so the commands that it will understand are different from the typical Unix or Linux commands. There are a couple of commands that are the same, but most are different. First thing to do is to ask it to show us the interfaces. And there you see the interfaces, and there are 12 of them starting at Ethernet 0 to Ethernet 11. There's also the loop back interface and then some switch interface. On this particular router, you can see that there is a network connected to Ethernet 0. There is a network connected to number 7, to number 8, and number 9. And then you have the typical loopback setup. If we ask it to show us its routing table, then I have to tell it to show us the IP route. There is the point at which we asked for the IP route, and what you can see up here are some codes. So the important ones for us are things that are directly connected, things that are statically routed, and then in principle, even though you won't see it in this particular setup, entries that are on this router because of the RIP protocol, things that are on this router because of the BGP protocol, and then quite a couple of variations of Ospf that may be on this router. Now, given the simplicity of the setup, in essence, one line going out to the internet and then a couple of networks, it is not too surprising to find that most of these entries refer to connections that are directly connected. That particular one that I've highlighted happens to be the local host entry, but the others are the three that go out to the three networks that are connected to the interfaces. And then you can see that there is a single static entry there, and that is the one that, again, deals with the default gateway. So if this router receives anything that is not intended for these known addresses, then it will send it out to that particular address, which it happens to know is connected to Ethernet 9. So only a single static route. The router is quite capable of completing the routing table by using RIP and all these other protocols. However, since there are no other routers on this network, there's no router that it can communicate with, that it can exchange information with, and hence there's no dynamic updating that can occur here. Perhaps one day I should set up another router so that I can give a better demonstration. As one final example, we can also look at the way in which packets are actually routed. So if I, for example, on a Windows machine, say trace RT, now on a Unix machine, that would be trace root, and you may even have to force it to use IP version 4 or IP version 6. But on Windows, it is simply trace RT, and then I tell it to trace the root to some fully qualified domain name or to some IP address. One possibility, since we looked at DNS.Google earlier, is to look at the path that we get from DNS Google, and we will find that it returns information about the various nodes between us and the destination. Some nodes won't respond. As you can see, node 2 there is not responding, but most of them should respond, and you can get a feeling for the path that this message is flowing. Very often one can interpret or infer things from the various machines, various computers on the network that are responding to this query. While it is busy doing this, also note that on some installations of Linux, you have to use the trace path command, not the trace root command. The speeds that we see over there indicate more or less how fast the responses are, and that tells you something about the network speed. Also, if you see a large number that suddenly pops up, then you may know that that is where a delay is in the particular context. Over here, since we've looked at the DNS.Google addresses, you may recall that it was mapped to 8.8.4.4 as well as to 8.8.8.8, and in this particular case, we traced the route to that particular node. Let us use our current knowledge to learn something about network routing, where the network routing has been, in a sense, broken purposefully. So here I'm connected to a Linux machine, and I am going to ask it to trace the root to frootservers.net. You will see that the output that we get is very similar, but it is formatted entirely differently. And wow, that was a quick response. And there you can see that that is our hop number 1. Our hop number 2, as I said earlier, you can infer some things from this. Hop number 3, hop number 4, and we can see that the machine that is responding to this last query happens to be in the .joburg domain. So F root servers in South Africa, from where I am at the moment in Pretoria, traces to an address, that particular address, in a .joburg, top-level domain, in Johannesburg, in other words. I am now going to repeat the experiment that I've just done. In fact, I'm going to execute the exact same command, but this time I am logged into a computer that is located in the United States. So it is very, very unlikely that it will trace its path to Johannesburg. And what you can see here is that, again, we are only a couple of hops away from that root server 7. The final machine that responds is indeed frootservers.net. There you can see that we are talking to something that is apparently in Los Angeles. And there we are talking to something that is apparently in San Diego. Node number 6 unfortunately doesn't give us any indication of where it is. But then we get to that particular address, which you can compare to the previous address. In fact, if we just quickly flip back and forth between these two screens, we can see that we are indeed routing to the very same address, but in the Johannesburg case, we end up at a slightly different address from the one that we specified as the target address. I'm going to leave this open for you to think about, and we may get back to this when we talk about layer 3. This is unfortunately the point up to which I can take you with my setup at home. In this video, we have considered the protocols that determine routes for network operation. Typically, they determine the routes and put the information in routing tables that can then be used by layer 3 to route messages, although, as we've mentioned, some other options also exist. The major distinctions that we made was on the first level between an interior gateway protocol and an exterior gateway protocol, and those two categories operate in the context of being inside or outside an autonomous system. In the case of the IGPs, we considered two protocols, namely RIP and Ospf, where RIP uses the Bellman-Ford algorithm with hop count as the primary metric, and Ospf used the link state, more specifically the Dijkstra algorithm, as its mechanism to operate, but in this case with varying costs or costs that can be adjusted so that we can get adaptive or dynamic routing. In the exterior gateway protocol category, we only briefly mentioned BGP and left it open for those who are really intrigued by the notions that we spoke about to get to know more about BGP. Obviously, it's hard to find a context where you can play with BGP because you in essence have to peer with someone else, with another party, to play with it. As we've said earlier in the video, our assumption was that you are familiar with the Dijkstra and Bellman-Ford algorithms, but we will cover them separately in 2 appendix videos, just in case you are not familiar with them. In our next major video, we will look at network management and a couple of related issues that also depend on protocols, application layer protocols, that are in place for the purpose of supporting the network rather than providing functionality that is useful to some end user.